Hey everybody, we're at week 1, or week 13. What am I thinking? Week 1. Set 1, SWYK 1. Might be a bad day, I don't know. Anyway, we want to talk about lots of things here going on. We'll start with factoring, stuff that has a, slide me over, stuff that has, why isn't it, there we go. Things that have GCFs. In this case, you can see that the GCF of x was pulled out. When we pulled out that x, that revealed to us a quadratic. That quadratic can be broken up into x minus 4 and x minus 3. Negative 4 and negative 3 multiply together to give me 12, but add up to negative 7, which is exactly what I needed. We set the factors equal to 0, x equal to 0. That's pretty boring. X minus 4 creates x equals 4. X minus 3 equals 0 creates x equals 3. So those are my 4 zeros. Now, once you get good at that, obviously, you're just going to say 0, 4, and 3. You'll know what to do, okay? But that's the nuts and bolts of what we're really doing. Another, similar situation, pull out the x, and then factor it into the remaining parts, x plus 5, x minus 4. And then you can look at it and say, well, you got to have a 0, right? You got to have a negative 5, and you got to have a positive 4. 0, negative 5, positive 4, that would be letter choice C. So just go about factoring those, pull out the GCF, and then continue on. Very similar to this situation, right? Pull out the x, we got this left over, we need to multiply together us to give positive 36, but add up to negative 12, of course that would be x minus 6 and x minus 6. Now both of those are the same, so we typically write it like this, x minus 6 quantity squared. Now, I'm going to do a little bit of work here. So obviously we can tell that the zeros of this thing are 0 and positive 6. Okay, the multiplicity issue is coming here. Let me draw a chart for you. So from this I made a chart. The zeros are actually 0 itself. That comes from the plain old x. And then 6 that comes from the x minus 6. We can see that the multiplicity, which is the number of times something repeats as a factor, well, the first x is all by itself, so that's a multiplicity of 1, which is odd, an odd multiplicity. And then the x minus 6 repeats twice. That's an even multiplicity. Now, I want to show you something that I've drawn a graph for you. And first we needed to use the leading term. The leading term here was x cubed. Because the leading coefficient is positive 1, that means the right-hand behavior is up. Because it's an odd degree, look at how odd and opposite almost look like reflected words, or at least the first 3 letters of opposite do. And then, so the opposite direction of the right, you have to know what the right is before you can tell me what the left is. So then I know that that side is down. Notice that I went to my graph. Now I know you didn't need to make a graph on this question, but I did anyway just to kind of help you understand some things that are going on. So we put our 0 and we put our 6 on the graph. When you have an odd multiplicity, it cuts through the axis. And I'll just try to abbreviate this. Cuts through. When you have an even multiplicity, it bounces off the axis. Okay? That one is actually noted in a song, a very popular song by, who was it? Katy Perry, I believe. I kissed the x-axis and I liked it. Okay, that is about the even multiplicity of a 0 or x-intercept on a polynomial. Now, I know you might not think that, but if you look at the words of the song, you will really see that she's really talking about this. Yeah, I know you think I'm crazy. Now, then they go on to say, okay, what is the multiplicity of the leftmost 0? Well, that's the 1. Right? And then the rightmost 0 would be the one that has the bounce. That's the 2. I know I did more on this question than you really need. I just wanted you to kind of associate the picture. So, complete the sentence. At the leftmost 0, the graph crosses the x-axis, right? That's that whole idea of cutting through the x-axis. And the rightmost 0, is bouncing. It touches the graph at the x-axis and turns around. Okay, that's the idea of the bounce. Next question. How do I know if something is a polynomial or not? Okay, well, I want to kind of look maybe at both of these questions at the same time so you can see what I'm talking about. A polynomial does not have breaks in the domain. For instance, here's a third degree polynomial. We could have another fourth degree polynomial that looks like this, but there's never a break in the graph. Even if it's, some fancy looking thing, it's a fifth degree polynomial, whatever, you never have a break in the domain of the graph. Okay? You never pick up your pencil when you're graphing it. That's how I know that this number 4 is a yes. But number 5 is definitely a no. There's definitely breaks in the domain. Now, we could have something like an absolute value function like that. That's a completely different. It's not a polynomial. It's got a real jagged edge right there at the vertex. So that would be something completely different. But even a linear function, right? Something like that. That is a polynomial. That fits the definition of polynomial. Okay, moving on. Oops, that's the end of this SWYK. We got a lot more coming in the future SWYKs, and they might go a little bit more than 7 minutes, but I'm going to do my best to try to keep them that way, to keep them short and sweet. Have a great day as you get to your SWYK.